Okay, welcome back. We are working on example 212 from the text, and I do have to fix a little mistake I had made when we started this problem in the previous video, and I wrote down this equation. I forgot to square this initial velocity term. This should be initial velocity squared plus 2a times y minus y naught. So our final velocity when the ball reaches its highest point is going to be 0. So that's 0 squared on this side of the equation. And on this side, the initial velocity that we throw it up with is 15. That needs to be squared. Okay, so that's it illustrates actually a very common mistake. Need to make sure that you don't forget either to write down an exponent or to actually, take it to the second power when you're solving it algebraically. These exponents have kind of a funny way of just disappearing if you're not careful. So make sure you're not overlooking anything, and make sure you're getting the equations written out correctly. So I'm just going to take this equation, I'm going to advance the slide so I've got a little bit more room to work here. Okay, so we had 0 squared, that's our final velocity squared, equals 15.0 meters per second. And we need to remember to square that, which I very nearly forgot, plus 2 times negative 9.8 meters per second squared. That's our acceleration, and it's going down, so that's why it's negative. Multiplied by our change in y, I'm just going to call delta y for simplicity for writing it down. So this is the equation we now need to solve for delta y. That's going to tell us how far up in the air we go. So delta y is equal to, let's start by getting this term over to the other side of the equation by subtracting it. So this now becomes negative 15.0 meters per second squared. We'll square it and then make it negative. Divided by 2 times negative 9.8 meters per second squared. Just the second squared there. Okay, and so this will be equal to negative 225 meters squared per second squared divided by negative 19.6 meters per second squared. So the seconds squared will cancel each other out, and when I've got meter squared divided by meter, that should leave me with just simply meters, which makes sense. That's what we're trying to find, is a height here. So delta y is equal to 11.5 meters. That's how high up in the air the ball will travel. So that answers the first part of this question, but it's a multi-part question. The next part of it asks, how long will the ball be in the air before it comes back to the hand? So now we've introduced time. Now we need to use one of those other constant acceleration equations to find out how long it's in the air. Okay, so I've jumped back to these constant acceleration equations, and so now that we want to know time, that is specifically what we're looking for, is how long is the ball in the air. We definitely want to be looking at one of these two equations that have time. There's t there, and there's a t there. So we need to look at the other variables and see if we know what they are. V equals V naught plus AT. Yeah, that works because we know the initial velocity. We toss it up in the air. We know that the final velocity when it gets to the highest point is going to be 0. We know the acceleration due to gravity pulling it down, and that leaves time as the only unknown variable. So, so this will definitely work. So let's use this. Okay, so I've jumped back to our example problem slide, and we said we were going to use the equation V equals V naught plus AT. Okay, so our initial velocity that we toss it up with is, oh, hold on a second. If I look at this problem here, before it comes back to the hand, so not how much time does it take to get to the highest point, but then how much time does it take to get all the way back down? Well, we can still use this equation, but what we have to realize is this is only going to tell us how far it goes from our hand to the highest point. Now, if we intuit the fact that it will take the same exact amount of time for the ball to come back down, we can still use this equation so long as we multiply the answer we get by 2. Otherwise, we could have used the other equation and just solved for it more directly. But I kind of like this approach. It's a much simpler equation. It just requires you to realize that it's going to take the same amount of time for the ball to go up as it does to come down. So let's get back to the equation now. So initial velocity is 15 meters per second. Nope, that's not right. Let's scratch that. The final velocity, v, is at the top. That's 0. So 0 meters per second equals the initial velocity when it leaves the hand of 15 meters per second, plus acceleration is going in the opposite direction as the velocity. Acceleration is trying to pull it down. So that's negative 9.8 meters per second squared. And then we have time. That's what we're going to solve for. So our time is going to be equal to negative 15 meters per second divided by negative 9.8 meters per second squared. So that's equal to 1.53 seconds. Now what we have to keep in mind is that 1.53 seconds is just the amount of time it takes to get from the hand to the highest point, and then it will take an additional 1.53 seconds to come back down to the hand. And that's what the question is asking for. How long will the ball be in there before it comes back to the hand? So as long as we then take this 1.53 and multiply it by 2, which gives us 3.06 seconds, this is a valid solution. It gets us 3.06 seconds in the air. Now, if you go and look at the PowerPoint I have posted on Blackboard that has the solutions typed out, you'll see that I took a different approach. I followed the approach used in the textbook, using the other of the 2 constant acceleration questions involving time. It's a little algebraically more difficult, but it still arrives at the same answer, same solution. Now, since we took the approach that we did, it kind of makes this part of the example a bit redundant because we've actually already figured this part out, because this is what we found in the last part, and we just doubled it in order to find the total amount of time spent in the air. So that is time equals 1.53 seconds. We already figured that part out. So let's move on then to the last part of this. What is the velocity of the ball when it returns to the thrower's hand? So we could prove this mathematically, but we could kind of intuit it as well. We could probably take a guess as to what this answer is going to be and get it right. I suspect, and I'm guessing that you might suspect as well, that if you were to throw a ball up with a speed of 15 meters per second, no matter how high up it goes, when it comes back down and reaches that same starting point, it's going to be going 15 meters per second just in the opposite direction. Let's see if we can prove that. So we know that we have an initial velocity of 15 meters per second. We have an acceleration pulling the ball down of 9.80 meters per second squared. We previously calculated that the time it spends in the air is 3.06 seconds. That's how long it takes to go all the way up and back down. That's the total time. So we want to know what the final velocity is. So if we take a look at those 4 constant acceleration equations, let's jump back to that slide. All right, so which of these equations is going to work for us? We have time, acceleration, initial velocity, and final velocity. I think this one might work out okay. Let's just look at the second one real quick. We do know we previously calculated how high it goes, where its starting point is, initial velocity it starts off with, and the time in the air. So really, I think either one of these could work. I think either one might work. Let's try them out. Let's jump back to the example. Yeah, like I said, I think we can use either one, and given the choice between them, I definitely think that the first one is simpler. V equals V naught plus AT. So the final velocity will equal the initial velocity of 15 meters per second plus the acceleration due to gravity, 9.80 meters per second squared, times the amount of time spent in the air of 3.06 seconds. And what is that equal to? Velocity is equal to negative 15.0 meters per second. So it works out. We proved our hypothesis using this equation that if we toss a ball up in the air at a given velocity, by the time it comes back down to our hand, it will have the same velocity, just in a different direction, negative 15. Okay, now I do want to point out here the quadratic formula. Now, I generally try to keep the focus in this class on the physics and not the algebra, but we really can't get around the algebra entirely. It is a useful tool for solving these problems. And occasionally, we may need to use the quadratic formula. In fact, in the following example, we will. So as a reminder, the quadratic formula is set up in the form of ax squared plus bx plus c equals 0, where x is the variable and a, b, and c are different constants. And we can solve for the variable x using this equation, negative b plus or minus square root of b squared minus 4ac all over 2a. Now, as I said, since the emphasis here isn't on the algebra, since the emphasis is on the physics, I don't mind how you solve your quadratic formula. Maybe you have a program in your calculator. Maybe you look up a website that'll solve it for you. Maybe you ask Siri or Google. It doesn't really matter to me how you do that part of the equation, but you do need to understand how to set it up in order to get the answer. So we'll do example 216 in the next video that will involve the quadratic formula.